So let's solve the harmonic oscillator by the method of action angle variables in the Hamiltonian formulation. At first, you write to the Hamiltonian the kinetic energy plus the potential energy, where omega is the frequency of the oscillator, and this is equal to the energy. Let's substitute now the momentum by the derivative of the generating function with respect to the coordinate. Substitute this momentum in the Hamiltonian, and you can solve now this equation to find what the generating function is. Isolate the generating function. Substitute now here this twice the energy by k squared, the reasons for which is going to be clear later. And thus you have the generating function, at least in integral form. Take the k out of the integral, and now this becomes simpler to solve by changing the variable. You have 1 minus something squared and the square root of that. This looks very similar to a trigonometric function. If you had 1 minus cosine squared of some angle, this would be equal to the sine squared. So let's make this substitution. Let's call this the cosine squared of an angle psi. So x itself is equal to plus or minus k over omega times cosine. Therefore, dx is equal to minus or plus k over omega sine psi d psi. So let's pick the negative so that all of the quantities are positive, and therefore the generating function becomes k times the integral of 1 minus cosine squared, the square root, so sine psi. Now substitute the dx by the plus k over omega sine psi d psi. So k squared over omega sine squared d psi. And this integral is simple to solve. It's a simple trigonometrical integral. You have k squared over 2 omega psi minus half of sine of 2 psi. So we found the generating function for the harmonic oscillator. We can now find the action. The action is the increment of the generating function over 2 pi. The increment as you go a full period to pi, that's the generating function as when psi is equal to 2 pi minus the generating function as when psi is equal to 0. So when psi is equal to 2 pi, you have that this is the sine of 4 pi, which is equal to 0. So the last term cancels. The first term is then k squared over 2 omega times 2 pi. And for s of phi equals 0, both terms are equal to 0. Psi is 0 and the sine of 0 also 0. So that's the only thing that you have, the first term. So the pi also cancels. And then you have the action. The action is equal to k squared over twice omega. And if you now recall that we wrote that k squared was twice the energy, then the action is equal to p squared plus omega squared x squared over 2 omega, which is then the energy over omega. So the energy being the Hamiltonian, we can write that the action is equal to the Hamiltonian over omega. That is, the Hamiltonian is the action times omega. Now let's find the angle now. Since we found the action, let's find the angle. So the Hamiltonian is the action times omega. Let's go back to the Hamilton equations of motion. J dot is equal to minus the derivative of the Hamiltonian over the angle. And the derivative of the angle is the derivative of the Hamiltonian over the action. The action is an integral of motion, so J dot is equal to 0, which sounds strange at first because the Hamiltonian does depend on the coordinate x, but it does not depend on the angle theta. We find the angle then by saying that omega dot is equal to the derivative of the Hamiltonian with respect to the action. The Hamiltonian was simply j times omega. Therefore, this is simply omega. And to find theta, we take the derivative of the generating function with respect to the action. Now, considering that the action is equal to k squared over 2 omega times this function of psi, and we saw that the k squared is twice the energy, then we can write then the generating function as the energy over omega times psi minus half of sine of 2 psi. Now the energy over omega is also the action, so we substitute it here by the action, and the derivative of this then with respect to j is psi minus half of sine of 2 psi plus j times the derivative of psi minus half cosine of 2 psi with respect to j. And using the chain rule here, this is the derivative of what is in parentheses with respect to psi. So that 1 minus the cosine of 2 psi times then the derivative of psi with respect to j. So what is the derivative of psi with respect to j? To find that, let's go back to our equation for x as a function of psi, which was this one, and we picked the negative. Isolate cosine psi, and the fact that the energy is k squared over 2. So then cosine psi is equal to minus omega over the square root of twice the energy in x. And the energy was the action times omega. So substitute that, and then we have that the cosine psi is equal to minus the square root of omega over twice j times x. We now take the derivative of this with respect to j on both sides. So what we have is minus sine of psi, this side the j, and then take the derivative of this with respect to psi, which is the minus the square root of omega over 2 times minus 1 over 2 j to the power 3/2 times x. And substitute again the definition of x with respect to psi, given by this equation. Substituting also k as its function of j. So what cancels here? We have square root of 2 here and here. We have omega up and down. We have a square root of j and a 3/2, so this becomes simply a linear j. The minus sign cuts with the minus sign in here. So we have a very simple expression then. This side the j is equal to 1 over twice j cosine of psi over sine of psi. Substitute that in the angle. This side the j here, substitute it, so the j cuts. And remember that 1 minus cosine of twice an angle, 1 you substitute by sine squared plus cosine squared. And the cosine of the double angle is equal to cosine of the square of the angle minus the sine of the square of the angle. With the minus sign, then this is minus cosine squared plus sine squared. So the cosine cancels, and this 1 minus cosine of twice of the angle is simply twice the sine squared. The twice on the sine squared would cut with the 2 in the denominator, and you have sine squared. Cut to the cosine, cut the sines. Now remember the sine of the double angle is twice sine cosine. The twice is going to cut, then you have sine cosine plus sine cosine, and that also cuts out. And then you have something very simple. Theta is equal to psi. So that variable psi that we introduced for convenience when doing the integral just to change the variable is in fact the angle variable conjugate to the action j. So we found the angle action variables for the harmonic oscillator. The angle is psi, and the action, which is an integral of motion, is the energy over omega, the period. From that, you also see that the period of the pendulum is constant, since j is an integral of motion and the energy is also constant.